welcome to Module 22 on descriptive statistics and distributions. This is going to be a relatively large module. We're going to talk about just basic definitions on statistical distributions and statistical ways of thinking. This is going to lead us into a little bit of a mathematical depth. And in particular, we're going to introduce probably one of the most important ideas in probability and even statistical scientific thinking, which is Bayes' rule. This is going to be a little bit of a stretch for this course. It won't be as crucial or much of an anchor for this course as other topics, but I wanted to spend a little bit of time talking about Bayes' rule just because of how important it is in real life in general. But it's going to be considered a stretch goal for us. And then, as usual, we walk through some worked examples with code. So by now, you should be increasingly comfortable with Python. You have experience with the pandas library. You have some experience with plotting, with matplotlib in particular. Because we're going to be going into some of the mathematics of probability, we're going to need to just remember our high school algebra, just some little basic functions, and you have to be somewhat comfortable with the idea of averages and percentages. By the end of this module, you'll be able to explain just verbally what a distribution is, why it matters. You'll be able to compute mean, median, variance, standard deviation, and something called interquartile range, or IQR, in Python in particular. You'll be able to look at a particular kind of visualization called histograms and box plots, look at their shapes, look at how they're spread over the image, and to derive information from them. Even though this is a bit of a stretch, you ought to be able to explain conditional probabilities at least, but hopefully including Bayes' rule. And then at the end, related to decisioning, you'll be able to choose summaries and metrics that match real-world decision-making processes and align sort of our mathematical thinking with real-life costs of error. So here's just kind of a motivating question for why this module. Imagine you have two instructors and both of them report an average exam score of 70%. And we want to know, are their classes doing equally well, or are they, equally around 70%? Imagine these are very tiny classes, Class A and Class B. The scores in the exam are out of 100. Here are the scores for the first class, Class A. Here are the scores for the second class, Class B. You can go ahead and confirm that the average of these numbers in each of Class A and B separately are approximately 70%. So the averages are the same. So if that's the depth of our statistical knowledge, then these classes might look very similar to one another. But if you just dig a little bit more, you'll see how different these two classes seem to be, right? Class A has scores that more or less cluster around 70. They go as low as 68. They go as high as 72, but they're all pretty close. Class B also has an average of around 70%, but you'll see there's 3 students who do pretty poorly. In fact, they all fail. And then you have these 5 students who get 100%, who think of this class as the easiest thing in the world. So Class A, everyone's kind of clustered around the mean. In Class B, there seems to be these 2 very distinct groups that interact with the class in a very different way. So, as I think we mentioned in one of the very first modules of this course, if we only look at the high-level statistics, we're doing a pretty poor job of understanding reality. A single number, like average in this case, will almost never tell us the full story, and what we really want is to understand overall distribution, the overall shape of the data. So we're going to define a couple of things here. A distribution is a description of how likely, or somewhat relatedly, how often different values or ranges of values occur when you sample them from real life. All right, so how likely is 70% on the exam? How likely is 100% on an exam for a particular sample of exams? A statistic is a quantity, a number, computed from a sample of data. Usually the statistic is a single number, although you may have multiple different statistics, all computing different things. A statistic is a single number, and it will summarize some aspect of the sample. So this could be something like a mean, a median, variance, IQR. We'll define all of these in greater detail shortly. Location or center is a kind of statistic that describes where the bulk of the distribution sits on the number line. So something like a mean, a median, something like an average. That's the center of the distribution. The spread, or the variability, is how dispersed the values are around their center. They could be, all the values can be very close to the center, like in class A in the previous example, or they can be spread out over a wider range. An outlier is an observation that just is unusually far from most of the data. Imagine class C has, almost all of the students get scores at around, 68, 69, 70%, but there's one student who gets 100%. That's unusually far from the rest of the data. That's an outlier. And the shape is a little bit qualitative. It's a little bit subjective. This is the overall form of the distribution. Is the distribution sort of symmetric around the center? Like, does it drop off equally quickly as you move away from the center towards the smaller values and towards the higher values? Or are there multiple different groups or peaks? We'll see examples of this shortly. We're going to build each of these definitions with an example, one with Python, which is always a lot of fun. Here, this is not for anything really. Like, again, these slides are essentially Jupyter notebooks themselves. So I'm going to need these libraries a bit later. We're going to need NumPy, Pandas, Matplotlib. Plotly is, I use Plotly a lot in these slides. Plotly has some aspects to it that make interaction a bit easier. That's beyond the nature of this course. I'm not going to ask you to do anything interactive, but just for the sake of these slides. And I set the random seed here. So, technically this is a math lens, but this is something that I think we all kind of understand. If we have a lot of observations called X, and each of these observations have different amounts, maybe we have one observation, X sub 1, that's a certain amount. We have another observation, X sub 2, that's another amount of whatever it is you're measuring. And then you have the total overall of the amounts we've measured. This is the sum of all of our measurements from the first measurement, I equals 1, to the last measurement, n. So we just sum up over all of the measurements we've taken. And then that gives us a total amount. If we spread it totally equally amongst everybody, we divide that total by the total number of observations, n, and this gives us x bar. So, the variable with a bar on top of it normally means like a calculated average. So x bar is the average here. There's not much to it you need from a point of view of code. Here is an example of a couple of x's. X sub 1 is 20, x sub 2 is 22, x sub 3 is 26, and n is 3, because there's 3 observations. I'm putting this into a NumPy array and storing that in XS. NumPy, being a library for numerical analysis, has a built-in function mean that runs on arrays. So I just call the function mean on the array XS, and I get my average, which is a floating point number, which is 2.2.6 continuing. So the total here is 68. The n is 3, so the average is 22 point approximately 67. No, I'm not trying to be, So the math lens, that was the mean. The median is a different idea for the center of a distribution, and in some sense it's a bit more robust, and it has more to do with the ranking of all of the observations we might have. Okay, when we observe things, so we might observe them in different orders. Sometimes we see big values, small values. They come in, at different rates. But if we were to take all those values and sort them, from biggest to smallest or from smallest to biggest, then the median is just going to be the middle observation in that list. So in this kind of cartoon over here, we have a lot of robot doctors. There's 9 of them. We've sorted them by height, so the value we care about, x sub I, is in terms of height. And then the robot in the middle of this sorted list, that's the median. Okay, so median, unlike mean, cares about order. And it won't necessarily, if there's big differences, if we had if this tallest robot was 100 times taller than all of the rest, it would still be the tallest robot, and it wouldn't affect the order of the ranking of these robots. So the middle robot, the median, would still be the same, even if this tallest robot grew 100 times taller, or even if this smallest robot grew 100 times smaller. So here's just another example. We have our x's and y's in these two lists. We can still compute the means of these lists, and we can compute now the medians. So NumPy also has this median function that runs over our lists. This is a little bit different than the previous example from the previous slide. So here I have an actual list, and I'm just calling .mean on that list to get my mean. On this example, I'm calling mean, well, here it is from the list itself. But when I'm calling medians here, I'm just calling it from the library, and I'm passing the list as an argument. Okay? These are two ways of computing these statistics, which I want you just to think about just for a brief moment. Here, I'm running a function on an object, and here, the function is in some sense called from the object. And in the second case, in the median case, I'm calling the function from the library, and I'm passing the object as an argument to that function in these parentheses here. Hopefully this difference is obvious and it makes sense to you. You can play around with this. Check if you can call xs.median. Check if you can call just see if you can call that. See if you can call np.mean with xs passed as an argument. Just see what happens. See if anything breaks or if you get the same values. Regardless, the main message here is actually these results. So as you can see from these lists, they're already sorted. The median value, the middle value here, is 22. So here's median is computed as 22 from the median function from NumPy. The averages are a bit different, right? So even though the first two values are the same in these lists, the third value is very different. We have someone that looks like an outlier here in 100. And the result is that the mean is relatively higher than in YS than it is for MS. It's an XS. So the mean seems to jump when we change 26 to 100. You can think about it that way. The mean jumps quite a lot, and the median stays the same. There should be a equal sign here. So when I post the slides, there should be an equal sign here between sigma squared of x and this 1 over n. These equations might be a little bit too in the weeds mathematically for this class in computer science, but I suspect a lot of you have already seen the definitions for variance and standard deviation. So the variance, sigma squared of x, is sort of the average expected difference, squared difference, between the mean of a distribution, x bar, which we computed a few slides ago, and each of the observations xi. Okay? So I've computed x bar over here. What is the difference between the mean and each of our observations? We square that difference and essentially take the average. So it's the expected value of these squared differences. That is the variance. If our x's and i's are very close to the mean, then this difference is going to be very close to 0, and then therefore our variance is going to be close to 0. But if our mean is at a certain point, but the x sub i's are spread out very widely, then the differences between those x's and i's, on average, will be very far from the mean, and then therefore our variance will be very big. Standard deviation is just the square root of variance. So a variance is sigma squared, standard deviation is sigma. Okay, and again, there should be an equal sign right there. In fact, what I'm going to do is I'm going to suddenly stop time, and a moment's going to pass, and then you're going to see an equal sign appear magically out of nowhere. Amazing. Here's our missing equal sign. Let's consider what I just mentioned a moment ago, and talk about the distribution, the spread of the data across all of our observations. So here we have two very simple arrays, A and B. The first one has 3 observations The mean is 20, right? The smallest one is 15. That's 5 less than the mean. The biggest value is 25. That's 5 more than the mean. Okay. In B, things are spread out a little bit further. Now the smallest value is 15 points away from the mean, and the biggest value, 35, is 15 points away from the mean. In some sense, all I've done is taken the 3 points in A and moved the outer points and then moved them equally away from the mean. Okay? So the result is that the means are going to be the same in each of these, and the medians are going to be the same also. But the standard deviations, which is the square root of the variance, increases a lot when I move spread my data further and further away from the center, from the mean. Okay, so I'm just calling the standard deviation function on my array A and on my array B, and as you can see, I have a smaller value for the standard deviation in A and a bigger one for the standard deviation of B. Okay, so the means are the same, but the distributions are either tight or spread out. So quantiles, yet another definition, sort of splits sorted data. So we have our data sorted just like we had when we're computing medians. We sort the data from smallest to biggest, and then we split the sorted data into parts containing specific proportions of the data. Okay, so the 25th percentile, or the first quartile, quartile sounds like quarter, 25% is a quarter of all of the data. The 25th percentile is the value at or below which about 25% of the observations fall. Okay, so we have all of our ranked data. The smallest 25% of the data will fall below the 25th percentile. The 50th percentile just means that 50% of the data is lower than this value. We already know what that is. We know that the median represents the middle value of all of our data. So 50% of the data, half of the data, like by definition, has to be less than the median. So the 50th percentile is the median. Just to continue, the 75th percentile means that's the value where 75% of all of the observations are below it. This is also called the third quartile because it's the third quarter of the data. 75% is 3/4 of the data. And that's more or less it. The definitions are pretty straightforward. When you hear percentile, just remember that it refers to a particular value below which that percentage of the data is to be found. The interquartile range, or IQR, is just the difference between these quartiles. So the third quartile, or the 75th percentile, minus the first quartile, or the 25th percentile, that is sort of 50% of the data. That's kind of between the 75% and 25%. Right? So obviously 75 minus 25 is 50%, and the range will be whatever value is at 75% of the data minus whatever the value is of 25% of the data. That'll give us the overall range of this middle 50% of the data. Here's how we can compute it. Here's a somewhat bigger array of data. All of it is sorted, as you can see, so you can kind of visualize some of these things. So quantile and percentile essentially mean the same thing. So Q1 is defined here on the array XS. I care about the 25th percentile, or quantile. And then I want the 75th percentile, or the third quartile. Store that in Q3. The interquartile range is thus Q3, the actual value, minus Q1. And then I print them all up. So 25% of these data, 1, 2, 3, 4, 5, 6, 7, 8. There's 8 values, so 25% of the data represents basically these 2 values over here. The first quartile represents the 10 and the 12, and a little bit of the space between 12 and 13. The details won't matter so much, but the value we get here is 12.75. The third quartile represents 6 out of 8 of the values that we have. So 1, 2, 3, 4, 5, 6, 21. So the computed quartile, third quartile here is 22. As you can see, 75% of the available observations fall under 22. So we're all good. And what is the difference between the third quartile 22 and the first quartile 12.75? That's just 9.25, which is the interquartile range over here. There's a couple of things which is probably confusing here. The first one of which is, well, why do we have 12.75 here when the second value I have here is just 12? This is a little bit beyond the scope of this class, but this is a statistical expectation. So it is still true that 25% of the observed values are below this quartile 12.75. The way that it's computed takes in the entire distribution into account, so it's not going to be exactly at 12, it's going to be a little bit higher, because we might sample other data in the future, and some of this data we might sample will fall somewhere between 12 and 13. We have an idea of what that distribution, the shape looks like, so these values aren't going to be exactly pinned to the observations we have in this list. But again, this is a bit too deep. Like, we don't need to know this for this class. The definitions are still good, right? So 25th percentile, the first quartile, 25% of the observed data fall at or below it, and that lines up. The second confusing thing is probably the terminology. I've mentioned percentile, I've mentioned quartile, and I've mentioned quantile. Now this is just a fault of the community. We have three different terminal words meaning two different things, and two of the terms are almost exactly the same in terms of how they're written. So quartile, as I've defined it, Q1, Q2, which is the median, and Q3. A quartile represents quarters of the data, 25%, 50%, 75%. Okay, that's quart with an R, which I've bold-faced it over here. And percentile kind of makes sense also because it represents a percentage. You can talk about an arbitrary percentage. The 27th percentile would be a value under which we'd find 27% of the observations. Okay. The problem here is, in terms of our terminology, is that in Python, a quantile refers to a quantity, and that quantity is essentially what we previously called the percentile. Okay. So this can be a little bit confusing, and because this is confusing, naturally confusing, there's noise here, we're not going to hyperfixate on it too much. If you sometimes, misunderstand what a quantile is and a quartile is, it's not the end of the world, okay? So don't stress out about that. So I just wanted to highlight that because I imagine some of you might be having a bit of terminology anxiety there. So I just wanted to visualize what we're talking about. So here's a number line in which we have observations. We have an observation at 10, 12, 13, and so on. These are 8 observations. The median doesn't necessarily have to be drawn from one of our observations. It's right in the middle. It's right in the middle of all of our data. Okay, so as you can see here, we have 4 data points to the left, 4 data points to the right, and the middle point between this observation here at 15 and this observation here at 20, the middle point is right there in the center of them on that line. The first quartile is down here. So just like we saw a moment ago in our example here, this is actually the same numbers from a few moments ago. Here are like the bottom 25% of our data, and Q1, the first quartile, 25th percentile, 25% of all of the data is below this line. Similarly, 75% of all of the data we've observed is below this line, the third quartile, which by definition means that 25% of the data is above it. And the interquartile range is just this shaded region between the third quartile and the first quartile. And what this is telling us is that, well, I expect 50% of all of my observations to fall within this range. And then indeed, there you have it. There's 4 data points which fall between the third and first quartiles. And that's more or less it. If the data is very spread out, if all of these data points were much further along the line in terms of smallness and much further along the line in terms of largeness, then this shaded interquartile range would spread out in both of these directions, and that would give us more or less a definition of spread. Interquartile range does ignore tails, though, right? So if for some reason this is not, visually to my eyes anyway, a value of 30 I wouldn't consider to be an outlier, even though it is quite far away from the other data points I've observed here. But if we just shove this 30, 100 points into 100 points higher to 130, the interquartile range would not necessarily change too much. It would be able to ignore these extreme tails, these outliers, right? Because even if this value over here was far larger, 50% of the data would still fall within this shaded range down here. So let's jump into a little bit of an example here. We have, again, kind of riffing on the earlier idea we had with regards to just having one statistic as if it represents all of the observations in our data. Now we're talking about hospitals, and we have 2 hospitals, and both of them say that the wait time is 30 minutes. And a 30-minute wait time would be fantastic across most hospitals in the world. Okay, so look at both of these representatives in these hospitals seem pretty happy. Would you rather go to hospital A or hospital B? If you were naive, you'd say, well, they both have the same average wait time. I guess it doesn't really matter which one I go to. Okay, as you can see, kind of behind the shoulders of these doctors, the actual reality seems to be a little bit different. So we were starting to gather some extra data beyond the initial statistic, and here's the actual simulation. I don't need to go into this too much. We're not really doing anything else here that is relevant to you. I'm doing a different sampling here. I'm sampling from a normal distribution and something called an exponential distribution, but for the time being, that's not going to be relevant to you. The only thing that's relevant to you here is the overall computed statistics. So hospital A and hospital B have means that are about the same. They're about 30 minutes. The medians, so if you sorted out all of the wait times for all the people who visited these hospitals and took the middle value, hospital A would have a median wait time of 30 minutes, which is close to the mean. Hospital B would have a smaller median of only 17.7 minutes. So the middle person, or the second quartile, I'm doing it. This second quartile, or the median, would be only 17 minutes. But look at the standard deviation, this measure of spread of the distribution. Hospital A, the distribution here, like the spread of the distribution in terms of standard deviation, is only 7.4 minutes, whereas the spread in hospital B is 30 minutes of spread. Okay, so what does this actually mean in terms of wait times? Well, we can go ahead and visualize it. So all I'm doing here is just plotting out the data that I used to obtain those statistics a few moments ago. Here's hospital A and here's hospital B. We have the means, which are dots, and the medians. Hospital A, they're almost exactly the same. They're both, the mean and the median are both around 30. And the standard deviation here of this shape of these wait times. So this is a histogram. So what this little bar over here means is just that there's about 26, I guess more like 27 people who have to wait around 22 minutes. Okay, and what this means over here is that there's 25 people who had to wait, it looks like about 28 minutes. Okay, so this is just like a count of all these different bins of weights. The mean and the median for hospital A is very close. This is the distribution drawn out for hospital B. Here we have the mean value, which is, over here in this dashed line. So it's still around 30. The median value is down here around, I think it was 17.7. So the median is a little bit smaller. But look at this spread. The spread of the data is totally different. We have a lot of people who only have to wait a very small number of minutes, like over 175 people, only wait, I don't know, it looks like maybe 5 minutes or something like that. But then look, this spread ends up kind of being spread out way into the future. So whereas into bigger wait times. So whereas in hospital A, you had a small number of people who had to wait 50 minutes, which is actually not that bad. In hospital B, you have certain numbers of people over here who have to wait 100 minutes, 125 minutes, and so on, right? That's crazy. So in other words, hospital A, most patients need to wait around 30 minutes. In hospital B, you have many quick visits, but a very long tail. So this spread we see here extending to the right is called the tail. We have a long tail of patients who have to wait far longer. Okay. So even though the averages seem kind of similar, certainly the means seem almost identical, and the medians aren't too far off from each other between hospital A and hospital B, the actual individual patient experiences are going to be very different. So when, again, you're trying to figure out if you're going to go to hospital A or hospital B, now you have a bit more information about what your experience is going to look like. In hospital B, there's a chance that you'll be in and out very quickly, but there's also a chance that you'll have to be waiting for a very long time indeed, multiple hours, in fact. So let's look at some outliers here. So an outlier, again, is just like we defined before, it's a data point that is very different from other data points. So here's just some code I used to generate this image. The code's really not important, but I like giving you the code just so you can play around with it yourself. But when you're playing around with it, don't worry too much about some details that aren't connected to the theory. So like we do animations here, we do interactive components. Like that's not part of what this lecture is about. So like don't worry about having to understand how to draw a slider or how to make a play button or something in a graph. That's obviously not part of this lecture. What we do have here, though, is a lot of wait times here. All these blue dots represent particular observations. This person had to wait 21 minutes. This person had to wait 23 minutes. And we have this outlier here who's we're going to move around a little bit. So far, we call this outlier. They have to wait 25 minutes. Not that bad. The mean is 21.4 in this data, and the median is 21. Okay, I'm just going to go ahead and slide this outlier further and further. So we have one person now who has to wait, let's say, a bit over 2 hours. You see, now the mean, as I'm moving the outlier back and forth, when I'm summing up over all of the wait times and then dividing by the total number of patients, that's the mean. The mean value is going to change, right? Because I'm including this outlier in my computation, so the mean is going to change a lot. So moving the outlier further and further away is going to drag the mean higher and higher. But look, the median is not changing at all, right? So all I'm doing, I'm leaving all the data the same except for this one person, which I'm fiddling with. I'm imagining that they have different amounts of wait times. That's very similar to my ordered ranking of robots, in which I was imagining that the tallest robot was like 100 times taller. The robot in the middle of that ranking wouldn't have changed their position. Similarly, the median in this list of wait times is not changing at all. The median is exactly the same as it was previously. Okay, so the mean will jump as we move the outlier, but the median actually doesn't change at all. I say barely changes, but it does not change at all. So again, conceptual scaffold, like where is what we're doing now in our overall pipeline? So like overall, we have like a phenomenon, like a health system. We have a data generating process. We don't know exactly what that is, but there's something in the hospital that's leading to these different observations in wait times. We sample a handful of wait times from patients in each of these hospitals. Now we're kind of here between these two boxes. We have our empirical distribution. We have the shape that we can kind of draw, that histogram, that bar graph, overall wait times. And then we can take some summaries. Now we can start taking means, medians, interquartile ranges, and so forth. And that's going to help us make our decisions. It's going to help us make a decision about which hospital we as a patient want to go to. But maybe one day you'll be an administrator at a hospital or in a hospital network, and it'll tell you, like, we need to focus on improvements in this hospital, or we need to figure out what's going right or wrong in that hospital. Okay, so again, data generating process is just a messy real world process. We're only ever going to see a sample. Those dots, we sample a particular set of observations. We don't see a true distribution. We don't have exact full knowledge of the universe that will tell us exactly what it is that causes the differences in these distributions. We just get the samples. But from those samples, we can compute some statistics, and that's going to inform us about the nature of the world. So let's get into some math, a little bit high level. This is going to be really simple, but also, in my view, exciting and fun. So let's think a little bit about the differences between probability and frequency. Sometimes we'll use those terms interchangeably, and just like we mentioned a moment ago, like the difference in these terminologies is not going to matter so much as long as like the meaning is clear from context. So frequency is more or less a measure of the samples, the specific measurements we've taken that led to the distributions. Like when I was talking a moment ago, I was saying, well, there's this many patients have this wait time that we've observed. That's like the frequency. That's the number of patients we've seen with that wait time. In this waiting room, we've sampled 1,000 patients in total, and say 230 of them have left without even being seen. This is our frequency. And we can compute sort of relative frequencies. So we can say, what is the proportion of these 1,000 patients who leave without being seen? Well, that's just 230 divided by 1,000, or 0.23, which sometimes we might even see, we might call that 23%, but this is still in terms of our observations. A probability model is subtly different, but often we kind of conflate them to mean the same thing. This is sort of a representation of what we imagine the world to be. And it gives us an estimate for a future observation. So in the probability model, given these samples that we've observed already in the past, we now use these proportions to make predictions. If a new patient entered the waiting room, there is a 23% chance that they might leave without being seen. You can see how this is different than the frequency. In the frequency, I'm just describing what I've observed previously. And the probability model is a representation of the real world, and it's helping me make predictions about particular observations I might observe in the future. In this case, the numbers are exactly the same, and for that reason, sometimes we conflate these things together. But it is a little bit different, right? Like if I've only observed 10 patients and not 1,000, am I that comfortable with my certainty that this percentage is meaningful and is an accurate representation of the world that I would call a probability, or that I'd be comfortable making this kind of prediction? That's a topic we'll come back to a bit later. So the idea here is that the data give us sample distributions, and the probability is a language that describes what we'd expect if we repeated the process many times. Okay, so it's really just a matter of how we describe these ideas, but also under the surface, there's a little bit of a difference in terms of how we even conceive of these ideas. So when we're talking about events, we can think about them in terms of the probability of those events, and we can think about running experiments. What is the probability of seeing a particular outcome? So here's another example. In a class, if I just take a random student from the class, what is the probability that they'll pass, or that they'll get a certain outcome, another outcome, right? So the sample space is like all of the possible observations I can have, and an event A represents a particular kind of outcome. So an event would be this student earns at least 80%, right? So I sample one of the students in this class, and I observe that they get at least 80%. I've observed an event in which the student earns at least 80%. Or if I'm looking at a different distribution over a different sample space, I'm looking over whether they pass or not. There's only two possible events. They pass or they don't. So I sample that space. I observe an event. I observe that they have passed. Maybe I sample another student. I observe that they did not pass. That's another event, which is different than the first. So I have these different events I can observe. But what is the probability of each of those events? If I was just to take a random student, what is the probability that they passed versus what is the probability that they did not pass? Or what is the probability that they get more, or at least 80%? what is the probability that they got less than 80%, and so on. This is really the subject of a course in which you'd want to get into probabilities much more deeply. So we're kind of dealing with it mostly at a intuitive level at this point. But again, we mentioned earlier that we assume you've seen high school probabilities, and you must have seen this in high school. The probability for a particular event A, of the kind we just exemplified, the probability has to be between 0 and 1. So the probability of any event you observe can be impossible. The probability is 0. It can be absolutely certain, that's 100%, or 1. And all of the probabilities we observe have to be somewhere in this range. S is the sample space over all possible outcomes. So either they pass or they didn't. I take the probability of passing, the probability of not passing. Those two probabilities combined or summed together is 1. Somewhere here also could have been this made more explicit. The sum over all possible events A and their probabilities will sum to 1. There's no way that I could take the probability of someone passing and the probability of someone not passing, add them together, and either not get 100% because there's no other event that I can sample that could make up for that missing percent, and it also wouldn't be more than 100%, right? Like if the probability of someone passing is 80% and the probability of someone not passing is 40%, that's impossible. Those probabilities don't add up to 100. It doesn't make sense. We have this terminology, which again, you've probably seen in high school, but I just wanted to iterate over this now. If A and B are disjoint, so they're mutually exclusive, the probability of kind of combining these together, taking the union of them, so this U is like the union set of two things together, is just the probability of one plus the probability of the other. Okay, so the probability of passing is 80%. The probability of not passing is 20%. Adding these two together is the probability of either passing or not passing, and that's the sum of those two probabilities. You could have many possible events. Like an event can be in the range of 0 to 10, from 11 to 20, from 21 to 30, and so on. Each of these events are disjoint. The ranges are all separate. So when you observe something, it would be one of these events only. And you can talk about the probability of someone getting in the 30s and the probability of someone getting in the 40s. The probability of those two events and add them together, ignoring everything else. Because these are disjoint, they don't overlap, then we could add them together in this way. The complement rule is sort of the opposite. So this is something we're not going to see very much again, but the concept will come up a little bit. So if the probability of if A is that they get 80% or above, right? So this is observation A. We have a certain probability associated with someone getting 80% or above. What is the probability that they don't get 80% or above? That is, they get 79% or lower. That's just the complement, right? That's just whatever probability is left over after we subtract out the probability that they get over 80%. So it's just like 100% or 1 minus whatever the probability is of that event. So it's sort of like taking the negation. The probability of observing a student earning 80% or above is the probability of A. What is the probability that does not happen? That's just whatever probability is left over, 1 minus P of A. Conditional probabilities. This is more the core of what we want to introduce and remind you of. The idea here is that we often want the probability of an event occurring, but given that another event has already occurred. And maybe these events, A and B, are not mutually exclusive like they are here, but sometimes it can occur at the same time. They're measuring different things. The probability A might be, say, the probability that a student is getting more than 80%. The probability B might be the probability that a student is studying more than 5 hours a week. It's measuring something different, so these probabilities are not disjoint from one another, but there's some relationship between these variables, right? Maybe if B goes up, the probability that a student studies more than 5 hours goes up, then maybe we expect to see the probability of earning more than 80% on an exam or on a course to also go up. Okay, so there's a relationship between these variables. We observe one, okay, we know that this student has actually studied more than 5 hours. That will change our estimate for what the probability of A should be. If we observe that they've studied more than 5 hours, then the chances that they will get more than 80% goes up. If we observe B, they've only studied 1 hour, they've observed less than 5 hours, then the probability of A will go down. The probability of them getting 80% or above will go down. Do you understand? So knowing B tells us something about our estimate for what A should be. This is the notation. The main thing here is this bar that goes up and down. We're going to see this a lot. This is like a fundamental thing in probability, and therefore it's a fundamental thing in data science. And therefore it's a fundamental thing in one of the most interesting areas of work in the world. Okay, so P, the way you'd read this is the probability of A given B. This vertical bar means given. Everything on the right is a variable that I actually observe. I've actually seen it, and then I don't know exactly what everything on the left is, but I have an estimate of what it is. I have an estimate for a probability. So here's a bit of a definition. So imagine that now B is not impossible. The probability of observing A, given that I've observed B, is the probability of both of them occurring at the same time, A and B, divided by the probability of B. So this upside down cup is an intersection. It's like a logical AND. It's like saying I've observed A and B at the same time. I'm going to draw this over here, right? So this is a visual representation of what we're talking about. It might be a bit easier over here. So we have like a sample space of possible observations. This orange circle, this entire circle, not just the Pac-Man subpart of it, but the entire circle, represents instances where A happens, like where the student gets 80% or above. B, the blue circle, including this overlapping bit, so the entire circle B, represents all of the observations of a student studying more than 5 hours. Okay? And the entire square here is all possible observations. So if I sample something out here, where my mouse is, this means that it's outside of A, which means that the student does not get 80% or above, and it's outside of B, which represents them not studying 5 hours or more. Okay, so everything outside of one of these regions is the complement that we saw before. And what is the probability of not A? Well, it's the entire space, the 100%, minus whatever this circle is. Or it's just basically it's white space plus this blue area. You can imagine just cutting out A. You can imagine cutting out, A is true, and everything that's left over is 1 minus A, and that space, it represents the probability of not A. We have an overlap here though, right? So this overlap here, any observation here represents a student who does get more than 80% on an exam, say, and because they're inside the A circle, and they're also inside the B circle, which means that they have studied more than 5 hours. Okay, so the probabilities here in this particular example is the probability of A is 60%, right? So 60% of the time I observe A, the big circle. This B over here, the probability of B is 40%. So 40% of the time I observe B. The intersection of these two things is 20%. So in 20% of all of my observations, you can picture all these observations that are all over the place here. 20% of the time, it's true that A, and it's true that B. So the student gets an 80% or above, and they've studied more than 5 hours. So this is the end, the the conjunction of these two things, the intersection of these two things. It all means the same thing. Here, down here, I have my definition. So what is the probability of A given B? Well, that's just the probability of their combination, the intersection between them, divided by the probability of B. Okay? And we can observe that sort of visually here. So imagine that you know that you're in this blue circle. You know that you're in B because you've observed B. Okay? You know that B is true. Therefore, you know that you're in the subuniverse defined by this circle. Okay? Now, you want to know what is the probability that A is true. Well, A is true only in this kind of shaded, salmonish kind of colored overlapping area here. Okay? This is the only part where A and B are both true. What is the relative proportion of A and B being true relative to only B being true and A not true, which is this leftover moon-shaped blue area here? That's just the intersection part, which is 20%, divided by all of the probability of B, which is 40%. So that's 0.2 divided by 0.4, which is 50%. If you observe that B is true, you're in this circle, then 50% of the time A will be true, and 50% of the time A will not be true. Another way to think about this is among all of the outcomes, when B happens, what fraction also have A happening? Okay, so hopefully this is getting across. Okay, so this is going to come up occasionally, the conditional probability of A given B. Okay, so it's called a conditional probability because we're conditioning on B. The condition that B is true, and now we're trying to readjust our estimate for what the probability of A is. Okay. Previously, with no information about B, the prior probability, the pre-existing probability of A was 60%. Knowing nothing about anything, I'd say 60% of the time, A would be true. But now I observed that B is true, and now I change my estimate for what the probability of A is. Given that I know that B is true, now I only have a 50% chance that A is true. You can see the difference between these quantities here. So we've talked a little bit about unions and intersections. So the union is A or B. This means like or both. So the union here is sort of everything that occurs within the combination, all the samples that are covered with either A and not B, B and not A, or A and B. So these three shaded regions all sum together to be the union of A combined with B. The intersection, the overlap between A and B, is basically end. That's this central region, this kind of salmon region. Here's 20%. And the general addition rule is, I put a box around it because this is important. The probability of either A or B happening is the probability of A happening plus the probability of B happening minus the probability of them both happening. Why is this the case? Why do I have to subtract this? Obviously, the union should be combining probabilities together, so what's up with this negative here? This can be kind of visualized again. So I want a region that either A or B happens, and again that could be A and not B happens, B and not A happens, or A and B happens. These three possibilities. Well, I can take the overall probability of A, which gives me this entire big circle, which includes this overlapping part. I add this B circle, this smaller circle, which includes this overlapping part. Now I've added this 40%, I've added this 20%, but I've also added this overlapping 20% twice. This overlapping 20% is part of the probability of A. It's also part of the probability of B. When I've added the probability of A plus the probability of B, I've added this intersecting part twice. So just to make everything kind of actually add up, so I'm not counting this middle region twice, I just have to subtract this middle region once. I care about its overlap. I want to count it once, but I don't want to count it twice. I just want to count each of these 3 shaded regions once. So that's why I subtract this overlapping intercept or intersection here. So it's probability of A plus a probability of B minus their intersection. So hopefully that's going to be clear. There's something called the multiplication rule, which changes to a chain rule. We'll see in a second. This refers to, again, the intersection of P, the probability of A happening and B happening at the same time. You can define this in a couple of ways. It's essentially, the probability of A happening times the probability of B happening, given that I've seen A. It's also the probability of B happening times the probability of A happening, given that I've seen B. So what is the probability of A and B? What is the probability of this overlapping part? Well, if I find myself sampling a point from this overlapping part here, this shaded region, that means that I kind of throw a dart at this board, and I have sampled somewhere in this big circle A. I've observed A, so I have the probability that my dart falls somewhere in this big circle. That's the probability of hitting the big circle A, but I'm actually care about the probability of A and B happening at the same time. So what is the probability that if I have a dart that falls somewhere in this big circle A, what is the probability that it also falls within this region here, this shaded region? This shaded region is just the probability of B happening, given that I know that I'm already somewhere in A. And the probability of both of these things happening at the same time, we have to take the product of them. Again, this is going back to high school, so it's more or less a refresher. So we won't get into kind of proofs as to why this is the case, but you can think of a logical AND being a multiplication in probability and a logical OR being a plus. So here we kind of have an OR. Either it's A or it's B, so we have a plus of these probabilities, we're adding them together. Down here, we're talking about, 2 things having to be true at the same time. It's true that I threw a dart at A, and it's true that given that I threw a dart at A, it also hit the region mapped out by B. This AND is represented by this product over here. This is kind of symmetric though, because I could throw a dart, I can hit somewhere in B. That's the probability of B. What is the probability that I've also hit A? That is the probability of A given that I've hit B somewhere. So what is the overall probability of A and B at the same time? That's the probability that I threw a dart and it hit B, and given that it hit B, it also landed in A. When I post these slides, these are going to be not just parentheses. This is the probability. If A and B are independent, if there's no information shared between A and B, then the probability of hitting A and B together will just be the probability of hitting A and the probability of hitting B. So that's the product between them. There's no information given that I've hit A. That doesn't tell me anything about the probability that I hit B, so there's no overlap. You can see here, it's as if I've taken this first expression here, probability of A times probability of B given A. Given that I've hit A, that doesn't tell me anything about the probability of hitting B, so this conditional kind of reverts to the idea of just the probability of hitting B. And the same applies here, so the probability of hitting B times the probability of A, given that I've hit B. Well, hitting B tells me nothing about A, so it just devolves into the probability of A. The conditional probabilities are 0. I want to mention that this A intersection B, the probability of A and B being simultaneously true, generalizes to more than just 2 events. So we have 4 events, A, B, C, and D. What is the probability that A is true, and B is true, and C is true, and D is true? We can represent this by these upside down cups, meaning intersection. It's somewhat a bit tighter to just represent them by these commas. So these commas basically take the place of these upside down cups. It just means and again. What you see over here, probability A, comma B, comma C, comma D, is just the probability of A and B and C and D all being true. And I can just go ahead and take the same sort of approach I took over here for multiple events and just spread it out. This is called the chain rule. So you can go variable by variable. This joint probability, the joint probability means like the probability of seeing each of these things, is a probability of any one of these variables times the probability of an other variable given that first one, times the variable, the third variable given that I've seen A and B, times the probability of the fourth variable given that I've seen A, B, and C. We can sample these in other orders. I feel like I'm getting into the weeds a little bit. If this is not clear to you what I'm doing, again, I'm reaching into your knowledge from your previous courses, but just let's talk about it if there's some ambiguity here. Here's one more example with probabilities, just to hopefully make this a bit clearer. Now I just have two variables, A and B. A and B are measuring two different kinds of things. A might have to do something with wait times. B might have something to do with how many doctors or nurses are on staff at a time. These are two kinds of observations I can have about an experience in a hospital. I can compute probabilities associated with each of these two separate variables describing different kinds of observations or events. And then I can say something like, well, the probability of A is 60%, the probability of B is 50%, the probability of both A and B being true at the same time is 30%. This overlapping area here. So again, if I'm throwing darts representing a sampling, like getting individual data points, a dart will hit both A and B 30% of the time. It'll hit A but not B 30% of the time. It'll hit somewhere in A 60% of the time, and so on. What is the probability that either A or B happens? Well, that's the probability of A, 30 plus 30, plus the probability of B, 30 plus 20. I've counted this 30% twice, so I need to subtract it. Subtract the 30. That gives us 30 plus 30 plus 20 minus 30, which is 80. Simple enough. Here these are not independent, right? So because the probability of observing A given B and the probability of observing B given A are not zero. Like they don't just devolve into the probability of B or A respectively. These variables are not independent. There's some relation between them. Okay, so they're not independent. There's an overlap. There's a relationship. Here's a little bit of an anti-example that reaches into our cognitive, like how humans think of things. We human brains are very bad at having an intuition about statistics, but the world is increasingly based on data. It's increasingly based on statistics. So we need to kind of overcome our biases, our cognitive mental biases. The problem is this, right? So we have two things we're measuring, two events. One event is whether or not somebody has a disease. Another event, another variable, is whether or not they test positive for the disease. These two things are closely related to each other. Having a disease, testing positive for a disease. You can see how these two ideas are closely linked to each other. And intuitively already in your mind, you're already saying, well, like those variables will go up and down with each other. So, the probability of having a disease and the probability of testing positive for those diseases should go up or down. If the probabilities are high for one, they should be high for the other. If they're low for one, it should be low for the other. So we just kind of conflate these ideas in our minds together. And we say that there's some kind of relationship between these two variables. And we don't know which direction that relationship is. So a common mistake would be that we'd say, well, the probability of having the disease, given that you've tested positive for the disease, and the probability that you test positive for the disease, given that you have the disease, we'd kind of conflate these two ideas together, and we'd imagine that they're the same probability, that these values are the same. These two things are related to each other. There's sort of a bidirectional relationship between them, and I'll just say that they're the same thing. But in real life, that's not the case. We'll see an example of this in a second, but that's just not the case. Like we already know, like mathematically, written down on paper or like visually in terms of those Venn diagrams, that these conditionals might not be the same. You can imagine moving these Venn diagrams around, and then you know that the intersection of observing both of these variables at the same time, divided by whatever variable we know about, whichever we're conditioning on, whichever's on the right of these bars, that will be different based on the probability of whatever we're conditioning on. Okay? So given that we know that someone's tested positive, that will tell us something about them having the disease. Given that they have the disease, that will tell us something about whether they've tested positive or not. But the relationship is not bidirectional, it's not symmetric. Super important, just from being a human being perspective, that's an important distinction to understand. So in data, you might know that 90% of people with the disease will test positive. That's this bottom proportion over here. So if somebody has the disease, 90% of the time they will test positive. So this bottom probability is 90%. But if the disease is very rare, then the problem of someone having the disease in the first case, given that they've tested positive, this can still be very low. So we need to be careful about this conditioning. The probability of A given B is not necessarily the probability of B given A in general. I'll show you an example of this in a second. But first we just have to talk about some, just wrapping up this little section, going back to means and medians. So we can construct a couple of different distributions that have very similar, they're very normal. They're very nearly like bell-shaped. One might be like right skewed a little bit, so there'd be many counts, many values where there's small counts, and a small number of people who have very big counts. And then we'll also have two different peaks. But all of these different examples, these three different examples rather, will have very similar means. Again, not for you to know at this point, but just for transparency, this is the code that I used to generate these different distributions down here. The means are all very similar. They're all around 30. So the normal is like a bell-shaped curve. Actually, I'll show you. That's this is kind of a bell-shaped curve. This is the normal distribution. Skewed is sort of like taking a normal distribution and then shifting it off to one side or the other. Here I've kind of squished it off to the left. So this is, we have like a small number of people over here with very big counts. So we have, 67, the value 20 occurs 67 times. The value 78 only occurs 2 times. So you can see how this distribution, the shape of the distribution is kind of shifted off to the left. And then the bimodal distribution, bi means 2, modal means kind of these different centers. There's 2 lumps over here. There's one big lump over here, and there's another one over here on the right. You can see how these distributions just visually are very different from one another. If we compute the mean and the medians for each of these, then, so, this is getting into the weeds a bit. We've already seen aggregations in a previous module. Here I'm telling aggregations get me the medians and get me the means and the medians. And then it just prints it up by the groups over here. So again, the coding isn't that important right now, but look into it. Anyway, the means are roughly the same, the medians are roughly the same, but you can see how different all of these values are. So the mean value over here is around 30, the median's around 30. The mean value here is around 30. The median, like the middle value here, is also around 30. The mean value is 30, and also if you were to like sort all of these observations, the one in the middle of the sorting, the median, would also be around 30. Okay. So again, I told you the mean. I've also told you the median. Actually, all of them are roughly the same, but we still don't know the like which reality we're in. Are we in reality A, B, or C? We might be in a calm reality in which most people get more or less the same kind of experience, which is exemplified here in this graph on the left. Or maybe I call it the horror movie over here, where we have a small number of people who seem to be relatively advantaged, and we have a lot of people out here towards the right which are disadvantaged with these high values of, say, wait times. I call that the horror movie, because who would want to live in that kind of distribution? Maybe we're in some other environment entirely. We still don't know, just from the medians and means, which of these realities we fall into. Box plots are a way to visualize the distributions of the data in a way that might actually give us a greater amount of appreciation for reality. So here's the code that gives us the box plots. So I'm getting a box from my Python library. Again, look into you don't need to know what's actually happening here. This is just provided to you for transparency's sake. You're going to have some work to do later, which is going to dig into this in one of the handouts. But for now, the most important thing is just visually what the data mean. This is sort of like looking at the data from the top down. So the distributions I saw on the previous slide, now we're looking at it kind of from the top down. And each of these points represents a sample point of data that was fed into these histograms, these distributions. And the width, the x-axis here doesn't really mean anything. I'm just sort of showing them spread out so it's easier to visualize what's going on. So here you have a big cluster, around 30, and more or less everything is tightly bound around 30. This is the skewed sample, where we have everything is kind of spread out in a non-uniform way. So you have a lot of values, observations with small values, but then you have a spread over more and more high values over here. So there's a longer tail going up into higher values. And down here, again from the top down, are two clumps. You're looking down at these mountains, at these mountains on the right from the top down. So what these box plots show you is a couple of statistics all at once, and it tells you the means and medians, but it also tells you something about the spread. So this middle bar here represents the median. So these are the medians, these bars in the middle here. As you hover in this graph on the actual slides, you can actually see the values pop up. The labels here are provided by me. The box plot doesn't know that this is normal. It doesn't know that this is skewed. I've provided these labels myself, but you can see it says the median is 28.57-ish, as this line over here. The bottom part of the shaded region is the first quartile. That means that 25% of the data is less than wherever this line is the first quartile. The third quartile means that 75% of the data is less than this value. Here it's 38.9-ish. And roughly you can visualize, it looks like 75% of all of these observations fall under this line over here. So we've just shaded this region. This interquartile range over here is this kind of light blue shade. The width of these boxes don't mean anything in this particular case, so don't worry about the widths. It's all about the heights of these things. And then we have these lower fences and the maximum. So the fence here actually is another statistic which we haven't seen yet. We'll talk about a bit later. But it basically represents, again, proportions and percentiles. And you can see that, everything is kind of more tight in the skewed case. So this bottom fence, I'm calling it, is closer to the distribution of my interquartile range. Everything is spread out, to higher values, to a much greater extent in the skewed case. So this upper fence is a bit further away from my interquartile range. And then we have maxes over here, just as these outliers over here. So now, just ignoring just the distributions of the samples and looking only at the box plots, we're starting to get a little bit of an understanding of what these distributions were, in a greater extent than just knowing the medians and the means. So the medians here, these lines in the middle of these boxes, are all very close to each other, but the interquartile range is quite a bit different. Right? So in the normal case, the normal bell curve, The interquartile range is pretty tight. The observations are pretty close to the mean or the median. So the height of these boxes is pretty small. In the other cases, where I have like distributions spread over two chunks, like in the bimodal case, or spread out very broadly into larger values, like in the skewed case, then this box is wider, meaning that I have a bigger spread. And also you can kind of see like where the median is within this box tells you about whether it's stretching towards the left or to the right. Okay, because this box extends higher, like away from the median to a greater extent than it extends lower from the median, you can tell that this distribution skews towards higher values. Very generally, like sometimes you see slight modifications to these as dot plots. We're going to talk about visualizations in a future module, so don't worry too much about details at this point, although you're more than free to play around with the details. The main idea here is that these shaded regions refer to where most of the data are around the center, in this case the median, and then the whiskers, those lines that kind of extend out of these boxes, represent sort of the more extreme data that's further away from the centers. So they help us compare groups a little bit. It might still be kind of difficult to tell the difference between some of these boxes, but at least you can tell that the skewed case and the bimodal case, you'll like if you're a random person, if you're a new patient walking into hospital A or hospital B or into a particular hospital, you can tell that your experience will be more varied in the skewed case than the bimodal case because these boxes are wider. And you'll also see something about the extreme experiences. So there's an extreme chance that you'll have there's an extreme chance you'll have a very long wait time in the skewed case as opposed to the normal case. Hopefully that makes sense. So now Bayes' rule. This is a stretch. This was not something I'm going to emphasize very much in the rest of this course, but it's one of the most fundamental ideas in data science and in probabilities. You might have seen this already also, but I really wanted to just bring it up here because it's so fundamental, and I would be remiss if I didn't expose you to some of these ideas. So, often we might know something about some prior beliefs of some variable x. So x is our events. We also know something about how likely data are under some hypothesis. So I say, well, given that I might know what x is, now I know something about y. Given, what is the probability of y given that I know x? What is the conditional probability of y given x? That's expressed over here. So I have some prior knowledge that tells me, I know what these distributions are, I know what these probabilities are. But imagine for some reason I observe y and I want to know x. Okay, this might be something like, well, I know that if somebody has the disease x, the probability of a test being positive y is something that I know. That's 90%. But now I want to say something about what is the probability that, given that they've tested positive for a disease, what is the probability that they actually have the disease? Again, we talked about that being the flip of, that's a cognitive dissonance that a lot of humans have trouble with. We know that these conditional probabilities of y given x and x given y are different from each other. But now I really care about x given y. I've observed y, but I want to know what x is. Well, the way to think about this is the probability of both of these things happening at the same time divided by the probability of y. Actually, a few slides ago, we've defined the joint probability, the intersection of x and y, as the probability of one given the probability of the other given one. Okay, so this probability of x and y is the probability of y times the probability of x given y, and I can just divide both of those sides of the equation by the probability of y, and that gives me this first equation over here, this first equality. Similarly, I mentioned earlier that I can take any variable initially, so I can take the probability of x and y and rewrite that in terms of, well, the probability of x times the probability of y given x. Okay, and then this is the end of Bayes' rule. This is Bayes' rule. This allows me to flip the conditioning. I know what the probability of y given x is. I know what the probability of x is. Maybe I know what the probability of y is, although as we'll see in a few moments, I don't necessarily need to know that to make decisions. And now I get the conditional probability that I actually care about now. What is the probability that given I observe a positive test, that they actually have the disease? Okay? I've walked through this derivation step by step. Okay? I said, well, I want to know one conditional probability. I know from the previous slide how to rewrite a joint probability of x and y together in two different ways. I just equate those two ways to each other, and I divide both sides by a prior probability, and this gives me Bayes' rule, which is this thing on the right over here. One way that I often tell people that they can use to remember this, and this is something I actually use myself when I'm just trying to write it out, is I look at the probability that I'm trying to get, x given y, and I generally know the form of Bayes' rule. I know that it's two probabilities divided by another probability. And this is a bit of a hack. This is a mnemonic that just helps you. But I say, well, I look at the variables in their order. It's x and then it's y. I'm going to take the first variable and put that in my numerator, the probability of x. Then I'll take the second variable, put that in my denominator. That's the probability of y. And I'll multiply that fraction by just a flip of x and y for each other. So looking at probability of x given y, that's the probability of x divided by the probability of y times the probability of y given x. And a way to remember that mnemonic might be to write this out a few times. When I talk about machine learning classes in upper years, often I'll tell students to just write this equation out several times on paper, and it might not be a bad exercise for you to do it yourself right now just to kind of get it. Again, Bayes' rule is going to come up a lot in the real world and in more like advanced classes in machine learning, so it's good to have some at least some familiarity with it now. This is going to help us go from a model to data, and from going from a data to updating beliefs. And I'm going to give you an example of why this is potentially important in a second. So here's just a Venn diagram from before. We have, and I don't need to, we talked about this before, so I can move on. So here's a story. I want you to think about this. You're walking across campus and you meet a nerdy student, okay? And you're trying to guess their program. In this kind of example, the question is, are they either they're a CS student or maybe they're an MBA student, okay? And the evidence, like we mentioned a moment ago, the evidence S is that they're shy and nerdy, okay? Now, we have a model in our brains already. We know that, well, given all the computer science PhD students we've seen, 80% of them have been shy. So given that I know that they're a computer science student, 80% of the time they'll be shy, okay? Now think about all the MBA students you've met, okay? Think of that set of people you know to be an MBA student. What is the probability in that group that they're shy? Well, only 20% of the MBA students you've seen have been shy. We know, again, this is a side note here, what this means is the probability of observing them being shy and being an MBA student divided by them being an MBA student in the first case. Now imagine also we know some prior probabilities. So the prior probability of C is 10%, and the prior probability of them being an MBA student is 90%. Okay, so their MBA students outnumber CS students 9-1. So what I would like, I'll fix these slides again later, is are they in CS? Okay, so you observe this shy student. Are they a computer science student? Well, I know that given that someone's a computer science student, there's an 80% chance that they're shy. Given that they're an MBA student, there's only a 20% chance that they're shy. So think about this for a moment, maybe pause this video. We talked about how conditional probabilities are not bidirectional. The probability of one given the other is not the same thing as the probability of the other given the one. Okay? So think about this, and let's jump to the answer. We have probabilities for them being shy given the program that they're in, but actually what we want from the question is the probability of them being a computer science student given that they're shy, and the probability of them being a MBA student given that they're shy. Remember, we're given that they're shy, like literally, we observe that they're shy. So we want to know what the probability of them being in one program is. We want to know what the probability of them being in another program and what that is. Okay, so because we've taken these probabilities, like S given C and S given M, we actually want C given S and M given S. We want the reverse of those probabilities to some extent. We know how to write them from Bayes' rule. So we know that the probability of them being a computer science PhD, given that they're shy, is the probability of them being a computer science student divided by the probability that they're shy times the probability that they're shy, given that they're a CS student, PhD student. And we can get the same sort of derivation, the probability of them being an MBA, given that they're shy. I actually kind of don't care, to make this decision, are they C or are they M? I just want to know which of these two fractions are bigger. Both of these fractions are divided by the probability of S. They're the same. The only thing that's changing is the numerators, the tops. So to make my decision, I can ignore the bottom. I don't need to know what the prior probability of them being shy is. I've already observed it. So all I need to do is compute the probabilities of these numerators, the top parts. So the probability of them being a computer science PhD, given that they're shy, is proportional to the prior probability of being a CS student, PhD student, times the probability of being shy times a CS student. I know that there's a 10% chance that they're a CS. I know that given that they're a CS, there's an 80% chance that they're shy, and I get the quantity 0.08. I plug in my known values for my probabilities in the MBA case. There's a 90% prior that they're MBA. There's a 20% chance that they're shy, given that they're an MBA, and the quantity I get is 0.18. You can normalize if you want. We don't necessarily even need to do that now. We already know that there's more than twice as much of a chance that they're an MBA student, given that they're shy, than there is that they are being a CS student. There seems to be a really strong relationship between being shy and being a CS PhD student, but given that there's so many more MBA students on campus, in this weird campus here, the chances of them actually being MBA is way higher. So these are the posterior beliefs of being an MBA student and being shy, we've computed, right? So, there's about a 69% chance that given that they're shy, that they're an MBA student. So even though shyness is more common among CS PhDs than MBAs, the random person you meet on campus is way more likely to be an MBA student, and even adjusting for these relationships, it's still more likely for them to be an MBA student. So this is a part of what I'm trying to do in this course is to give you tools and experience that's going to help you in the future in your careers, but also this is a super interesting area of just thought, right? Statistics, probabilities, making real good decisions in the real world is something that so many people, especially these days, seem to be having trouble with. And if we can think more in terms of Bayesian statistics, in terms of true statistics, then this will help us just be more functional members of society. No, I don't mean to oversell it too much, but I truly believe that that's the case. Okay. So making decisions based on probabilities, we have to remember some priors, right? Base rates matter. If you ignore the prior probabilities of C and M, you might overtrust how typical the person looks, right? If all you're doing is fixating on these apparent relationships between shyness and a program, then you're throwing out really crucial information about the real world. There's also this likelihood versus the prior. So the probability of shyness given that the program that they're in describes how evidence behaves under different hypotheses, and this is what we call likelihoods. These are these conditional probabilities. And the prior probabilities are just how common each hypothesis is before we even look at the evidence in the first case. So the posterior, the thing we're actually looking for, the evidence, posterior means after we combine things, is the prior probability times the likelihood of the evidence under the hypothesis. And this core idea is a skill that I think many people lack in the real world. But, again, the real world is fraught with challenges related to the economy, related to the spread of disease, related to other aspects of a functional society we need to understand how these different quantities all relate to one another. We also want to be able to update our beliefs. Again, this speaks to the real world phenomena of people believing something and then never changing their belief about that thing. And we don't need to get into the details of that, but I can sure you imagine somebody who seems to believe that something is the case, and no matter how much evidence you give them, they just never shake their beliefs of that thing. And as you are imagining right now, you can see how much of a problem that can be. Okay? Bayesian thinking encourages you to go through this loop. Okay? You start with a prior belief, this idea that CS students are usually shy, but then you collect real data. You collect how shy students actually are in your classes, and then you use Bayes' rule or something like it to update your beliefs. So you're going to continuously update your probability of shyness given a program, and you'll look at the distribution of students across your campus, and you'll update the prior probabilities of observing whether they're a CS student or an MBA student. Okay. Because year after year, there might be more or less CS students and more or less MBA students. So these are pitfalls to avoid both in specific instances of doing data science, but also just being a human in society. You want to avoid confirmation bias. Another problem that humans seem to have, like I mentioned earlier, we seem to conflate those two different kinds of conditionals with each other. Human beings also, we just want to believe whatever we already believe. So if we believe that CS students are shy, and we observe an MBA student being shy, we'll tell ourselves, well, that doesn't really have anything to do with me. I don't care about that because my mental model is about CS students. Or if you see a CS student who's really outgoing and really personable and extroverted, you'll say, well, this is an extreme case. This is an outlier. This doesn't fit my model, therefore it must be wrong. Like the real world is wrong, but my model is right, so I'm going to ignore that noise because it contradicts my expectations, my model of the world. And this is a confirmation bias, and that's a problem that humans need to get over, right? So you need to acquire all this data, and you need to subtly, even if it's only by one small point at a time, update your mental model for whatever it is you're measuring. So you need to keep on updating these probabilities with new observations. It's not just a quirk for this class. It's a true aspect. It's a true effect of like the real world that you need to consider. Okay, so again, one of the reasons why I think this course is so important is not just that it's going to give you an interesting career in data science or give you lots of opportunities that others who don't take this class might not get, but it teaches us something about how we try to find the truth in the real world. And I'm sorry if that sounds cheesy, but like I truly believe that to be the case. So good Bayesian way of thinking is sort of like taking note of what you expect before you look at the data, actually acquire the data, compare any surprise you have, don't ignore it just because it seems weird, and then keep on sort of iterating and updating carefully. A few more examples. I'm going to go through this relatively quickly now. So daily step counts again. Imagine we have a health app that chooses who gets an email saying you need to exercise more. Okay, here's some code that generates the data. We have the age of the person using these apps. So they're 45 years of age, 51 years of age, and we have whether or not we have this being derived from a watch or derived from a phone. So in this case, this watch has gotten about 9,700 steps for this 51-year-old. And this phone has gotten about 11,300 steps on the phone for this 45-year-old. We can compute the statistics. So as we saw in a previous module, that when we have a data frame, and here I'm looking at just the column, I'm only caring about steps at this point, so describe the steps of our data frame that we defined in a previous slide. Here I say the percentiles I care about are the 10th percentile, the 20th percentile, and so on, and describe it. So put that description in summary steps. Here I'm just doing a pivot. So the details here don't matter so much. What matters is the descriptive statistics I get. I have 600 observations. The mean is about 7,800 steps. The smallest number of steps someone took is 1,255, and so on. We see a couple of things. So the mean is kind of close-ish to the target of 10,000 steps, sort of. 50% of the observations I have are at or below about 8,700 steps. 90% of the data I have observed is below 10,870 steps, and so on. We see a couple of things here. So 10% of the data, 20% of the data fall into this really low activity group. So we see only about 4,000 steps for the bottom 20%. And this is quite a bit different than 50%, right? So there's a non-trivial collection of people who are in the low activity group, which we might need to consider as people we need to ping for reminders to exercise. Here's the distribution of the data. So the histogram is this sort of bar graph I see at the bottom. This is just going to show me the counts for each of these little bins. And that's all that you really care about. I'm showing the marginal distributions. I'm saying I want to see this box distribution, which we defined a few slides ago. Previously, that box distribution was like in the y-axis, and here it's being spread out over the histogram. But the core of it is the same. We have the minimum values in the lower fence. We have the first quartile of data. We have the median over here. The shaded region represents the interquartile range between the third quartile, the 75th percentile, and then the first quartile, the 25th percentile. So 50% of all of the data falls within this range of about 4,780 to about 10,000, and so on. You can see that there's two groups over here. This is a bimodal distribution. I have a big chunk of people who fall under the 25th percentile who don't seem to be doing very much at all. And then I have another big chunk of people who might be more typical users of the app. So this left tail over here are people who never even hit 6,000 steps. And this box plot shows this asymmetry kind of clearly. The median is way over here, but the distribution seems to be spread out towards this left. Like this box, the shaded area seems to be a lot wider going towards the left. There's a bigger difference between the first quartile and the median than there is between the median and the third quartile. Are there any outliers? Can you tell that from this graph? That's something for you to think about. So we want to flag users who might benefit from a nudge. This is the bottom 20 percentile on steps. So yeah, we want to missing a truly low active user. This is a false negative. So this says, well, this low activity user is we imagine that they're not actually low activity, but that's false. That is missing that person is worse than saying someone who's actually moderatively active. Saying that they're a positive. That they're low activity, so they're positive in that sense. Getting that wrong, giving them a nudge, it would annoy them. The cost of a false positive, the cost of a nudge would be something, but missing a truly low active user is worse in our current conception. Okay. Regardless, here I'm just taking the quantile, which we defined earlier is means the same thing as percentile. We're taking the 20th percentile. This is the threshold defined by the 20th percentile. That's about 4,431 steps. How many people are flagged? So out of all of the data in the steps column of my data frame, I can compare that value against this threshold, which I've defined as the 20th percentile. This is a binary decision, so now I have a vector of ones and zeros. So if the person's steps is less than or equal to this threshold, it's 1, it's true. If the person's steps is above this threshold, I don't need to flag them false. They're not a low activity user. I have a bunch of ones and zeros. As we talked about in an earlier module, the average or the mean of all of these ones and zeros is just the proportion of ones I have in this entire vector of numbers. What this gives me is actually the proportion here, coincidentally, or maybe not coincidentally, is the proportion of people I flag as being low activity, rounded to the nearest 2 decimal points, is 20%. Is this percentage too big? Is it too small? So first of all, is this like 20%? Like, is 20% of the people who are flagged as being less than or equal to this threshold? Is that surprising? Is it by definition? Make sure you can answer that question properly. We talked about it way at the beginning of this module. Is 20% too small? So again, like being the decision maker now, being like the developer of this app, taking the bottom 20 percentile here, like, does that make sense? Maybe I should have taken something like a 30th percentile. Is there some other computation I could have done to determine who should be flagged and who shouldn't? That's more of a decision-making process that you can just consider. There's no right or wrong answer for that. Here's another example. So back to hospitals, we have a regulator now. The regulator cares about wait times. They want to know if wait times are distributed fairly, or if there are certain subgroups that consistently have to wait longer. We might already know that there's a difference between hospitals A and B, but we have patients coming from all kinds of different neighborhoods to these hospitals, coming to hospitals A and B separately, and we want to know maybe some people from a particular neighborhood are disadvantaged at both hospitals. Maybe they're disadvantaged at only one hospital. This will tell us something about any kind of like demographic bias that we want to avoid, right? Again, you're a decision maker, you're at a hospital or a hospital network, as some of you might be eventually. This is the kind of question you want to ask. Is there some kind of demographic bias going on in my hospitals? How you determine that is going to be through probabilities and statistics of the kind we've been measuring before, and we're going to dig into that right now. So I've generated data, which I'm showing you how I did that here. I have now a bunch of observations from patients. So we have this table, this tidy table, where the first observation, we see somebody waiting for 29.36 minutes. That person lives in neighborhood A and they go to hospital A. This other observation here has a wait time of 37.57 minutes. They come from neighborhood C and they go to hospital A, and so on. This is my raw observations. I'm just grouping summaries. I've talked about how to do this before, but grouping by silos according to some label in data frames in Pandas is done by this group by function. So we talked about it before. We don't need to get into it again. And the ag basically tells us like what is it I'm trying to aggregate over my silos. In a previous slide, in a previous module, I think we just looked at means. But here I'm saying within every silo, within every combination, I'm looking for counts, and I'm looking for means, and I'm looking for medians, and I'm looking for standard deviations. These strings matter because I'm telling the aggregation that I want to do these computations, so run the function count, run the function mean, and so on. I'm also, by the way, like I'm looking over not just one group, but I'm looking over combinations of groups. So I care about each combination of hospital and neighborhood. And the thing I'm measuring is still wait times, and then just print it out at the end on line 7. So I spent some more time than I thought I would, but I want you guys to know how to do this. So here's the result of doing this group by. I have all the combinations of my groups. The variables were hospital and neighborhoods, and I have all of my statistics that I computed, counts, medians, and so on. So I have, what this is saying is I have 188 data points of patients from neighborhood A going to hospital A. I have 142 patients from neighborhood B going to hospital A, and so on. For all patients from neighborhood B who go to hospital A, the mean wait time is 30.9 minutes, the median is 30.6, and the standard deviation is 6.9. So that's kind of a descriptive statistic. So you're like a CEO of a hospital or hospital network right now. You get a report on your desk, and it gives you descriptive statistics like this. And because you're a smart person, you're starting to dig into the data, and you're happy that you got more than one statistic. We talked about why that would be a problem. You have means and medians. In a previous example, these were very similar, but in this example, you can see how well the means are all very similar. Hospitals A and B are still reporting, means of about 30 minutes. So the hospitals A and B look kind of similar to each other. But now we have medians that suddenly look quite a bit different. So first of all of the medians for hospital B are lower. So the median is lower than the mean. What we remember seeing when we were sliding the outliers back and forth, that when data is distributed towards the right, the mean will get bigger and bigger, and the median will stay the same. It can stay pretty small. So already what you're seeing right now by looking at just this table is that, wait a second, like hospital B seems to be exhibiting this idea that we have a small number of patients across neighborhoods A, B, and C who have very short wait times. And then we have lots and lots of individuals who have longer and longer wait times. Like it seems to be stretching out towards the right. You also see the standard deviation. That's just a measure of spread in the data. And in hospital A, everything's pretty tight. The number is pretty small, so the variance is also small. It's around the mean. Whereas the standard deviation in hospital B is much wider. Like your experience in hospital B will be much more varied than in hospital A. So here's a little interactive widget. This is basically showing us a box plot as before. It's not really showing you anything different conceptually than we didn't see before. It's just comparing their two hospitals. So hospital A is in blue, hospital B is in red. And each of these data points represents an observation, a sample, a patient. So you can see here, if somebody comes from neighborhood A, first of all, let's look at the hospitals again. So I mentioned earlier that hospital A seems to be a bit more consistent, and hospital B seems more spread out. And that's what you can see that across neighborhoods. So across all of the neighborhoods in blue, hospital A, the variances are tight. Those blue boxes are pretty small. And you can see the distributions are also pretty tight. And in hospital B, the red hospital, things are much more spread out, and the box plots are also wider. They're spread out towards the higher end of the spectrum, right? So the box plots, like the medians, are kind of low in these box plots. They stretch out, more towards the top, meaning that things are stretched out more upwards, and that's the case of our distribution. And then you have these whiskers over here, and the whiskers are spread out quite a lot more broadly in hospital B than hospital A, and this seems to be kind of consistent across whatever the neighborhood you're in. So, high level, this is something which kind of does have a right answer. Which hospital looks more variable overall? I think 100% of you is going to get that question correct. Which neighborhood was worse off overall? So now looking at just A and C and B here. I don't know why this ended up being in the wrong order. But looking across where people are coming from. Again, you're making a decision, is there a bias against where people are coming from, what their neighborhood is? And, the general pattern of A versus B, hospitals A versus B, blue versus red, is more or less consistent. But maybe there's something, maybe the spread is a bit worse for one subsection of the population than another. And I'll just leave that for you to consider and think about and write down in your journal. If you think about ER weights and think about tails, then the harm that is delivered to individuals will live in longer weights. So if you look at a measure that is sensitive to longer wait times, so imagine the 90th percentile. So the 90th percentile means that 90% of the data will be less than this value. In blue, 90% of the data will be somewhat low down here with a relatively low wait time. 90% of all of these observations are pretty low. But 90% of the observations in the red hospital will be pretty high, right? 90% of the data will fall under higher values in the red hospital. And that's what we care about, right? We really care about people having to sit in the waiting room and having to wait for a very long time. That does some material harm to people. So all that's going on in this little code base is I'm just saying, group by a combination of hospital and neighborhood, look at the wait times, and now I care about the 90th quantile, which we learned is the 90th percentile, and then just show it to me. So P90 is our data frame. And here it is. Sorry, one more thing. Unstack basically separates out hospital from neighborhood. That's why I get like neighborhoods in one dimension and hospitals in the other. That comes from the unstack function. But now again, you being a decision maker at a hospital can look at these 90th percentiles, and you can see, well, like the people we can be harming with long wait times. There doesn't seem to be very many people with long wait times in Hospital A, regardless of whether they come from neighborhood A, B, and C. Now in Hospital B, if they come from A, B, and C, like the 90th percentile will be higher. So B generally has, like the red hospital has these big spreads. But if they come from neighborhoods B or C, suddenly now 90% of the data falls below 80 minutes or 85 minutes. Right? These are the people who have to wait a very long time. And a lot of people are going to have to wait a very long time if they come from neighborhoods B or C. So we've kind of identified our question. So we've kind of we've discovered what we're looking for. There seems to be some kind of bias going on in Hospital B against people who come from neighborhoods B or C. And now you, being the decision maker, can do something about it. Okay? This is the important bit. So again, like most of our examples are trying to mapping to these real world phenomena that like have some ethical component, and hopefully you can see how we've let me see if I can. There you go. We've done that. We've found sort of this problem using statistics from today's module. So just a little bit of this. So again, like big picture for the STEPS app, we care about the bottom 20% of people, like people who are not walking very much. We want to help them walk a bit more. So we want to give them nudges. And we have a cost associated with that. We talked about, giving nudges to people who don't need it. There's a cost associated with it. Not giving nudges to people who do need it, there's a cost associated with that. That was a bigger cost to us. We want to nudge people. So, we had that cost rationale, and we're looking at the bottom 20th percentile. In the ER fairness problem, the main issue we wanted to avoid is long wait times. The long wait times was defined by the bigger percentiles of 90th or 95 percentiles. So we walked through that. That represented people waiting a very long time. And, the cost was, the costs are associated with long waits. Long waits can mean that there's harms, the people will have a bad experience, they'll complain, maybe they'll learn not even to go to the hospital in the first case because they'll be waiting so long. I'm extrapolating a little bit, but you can see how, like, what kind of real world costs are associated with that. The good thing is we've kept our science hat on. So even though you've temporarily become a CEO of a hospital, or you've become like a CTO at a little startup building these apps, these step count apps. You being a scientist means that, well, we started making claims about percentiles and statistics, but we can test it. We can keep on getting more and more data, and we can see to what extent our predictions about whether or not the distribution of data stays the same. We can measure that by just gathering more data and computing new percentiles and looking at how much they change from one sample of data to the next. Again, so the averages, like on average, things can look very healthy. The average wait time in hospitals A and B are the same. Even the medians are somewhat the same, but this can hide people who are struggling, and this can hide whether there's some small groups that are super advantaged compared to others. So again, simple statistics can hide disadvantaged groups, and it can hide dangerous tails. I think I might have mentioned a little bit about economics. Often you'll see things like the stock market by itself, like the TSE, the value of the TSE, the Toronto Stock Exchange, being high or low, being a single statistic representing the economy. People seem to fixate on that, or they'll look at something like GDP. They might even look at GDP per capita, and that feels like it's as a single statistic that should be meaningful, right? It means something about the overall productivity in terms of domestic product across a population, the GDP of the province of Nova Scotia, the GDP in the province of Ontario, even divided by population per capita. But that can sound like it's computing something meaningful, but you're ignoring, all you're doing is fixating on a single number, the actual distributions. You might have seen GDP per capita on provinces across the country of Canada, and some provinces that have high unemployment rates can still have very high GDP, and even GDP relative to the capita, because some people in that province make an absolute ton of money, maybe because they have like exclusive rights to mining or resource extraction. So the distribution of people's wealth will be very skewed. The average income can still be pretty high, but the distribution will be very different depending on if it's very unequal versus if it's more diversified, more equal. Okay? So I wanted to mention that as a moment. This is one of those things that comes up in real life, like the economic productivity of a country or a province or a city. In the real world, people fixate on averages. The average is this. That tells us everything we need to know. That's not the case, right? Those people lack what you now know about statistics and reality, which is that there's distributions that can give you very similar statistics or misleading statistics based on different distributions below the surface. So always look at distributions. Always stratify things when equity matters. So if there's something about subgroups that matters, you really need to take that into consideration and document all the time and make your observations clear and explicit. So that was a big module. A big part of it in the middle was more just for your future knowledge, and it's less to do with this class, but I think that's important. And that was with regards to Bayes. The important parts of this module for this class are about distributions. We talked about statistics, which are kind of compressed descriptions. We talked about means and medians. We talked about how one is more or less sensitive to outliers than the other. We talked about variance and standard deviation. We talked about interquartile ranges and how those are ways that we can measure the spread. It's better to have measures of spread than just having measures of means or medians, but still usually you'd rather have a histogram. We looked at box plots, which visually tell us something about how the distribution is shaped. It kind of summarizes that for us. And then we also talked about Bayes' rule. I mentioned the Bayes' rule here because now we're talking about probabilities and distributions, and we took a bit of a side note into Bayes. We're not going to have much of a chance to see it again, which is why I put it in this module. It's not going to come up that often, so we're not going to test you over and over again about Bayes, but we are going to see conditional probabilities and just the mere skill, the life skill of being able to think of one probability given knowledge about another one is something that's going to be crucial to your success as a data scientist, but it's also going to help you make better decisions and better understand the real world than your peers. And I'm sure you can go online now and look at your feed and look at people talking about real world challenges, and you can maybe even spot, oh, this person didn't think in terms of Bayesian statistics when they said this really silly thing. And now suddenly you're smarter than a lot of the people that you see online. Here's a quick check for you, so please go through these to make sure you kind of understand the topics from today. If you're struggling with any of these, bring these to class, and I'm happy to discuss it. Thanks so much for sticking it out, and this is a very important module for me because of how much of a relationship it has with real-world reasoning and your cognitive abilities. So thanks so much to you for paying attention. See you next time.